Assalamu alaikum. We are continuing our discussion on steady state error design via integral control. The theoretical part that the derivation of the required equation based on the insertion of a pole at the origin to minimize finite steady state error to zero steady state error is already done in the first part, a small theory related to that one. So now today we are going to see how we are going to do the actual designing. So for that, actually, this is the existing block diagram as well as the required equation that we have. Now, what we are going to do in this session is basically we're going to solve one example. Example 12.10. System is given x dot equal to 0, 1, minus 3, minus 5, x plus 0, 1, u, y equal to 1, 0, x. So by looking at the equation, you should have realized that the system is represented in the phase variable form. So the problem has actually two sections. The first one is asking you to design a controller without the integral control, and that is part A. Part A, design without integral control. And the specifications given is 10% overshoot and settling time TS to be 0.5. So after designing the controller, the control systems, for that one, we have to find out what is our steady state error E infinity. Okay, so let's proceed with the design, and then what is the existing system steady state. So from the given parameters, we have 10% overshoot. So we can find out the value of the zeta. Zeta is minus ln 10%, basically 0.1 divided by root over ln pi square plus ln 0.1 square. So that will give us a value approximately 0.591. And also the settling time is given. So for approximate formula for that one is 4 by zeta omega n, which is 0.5. So from that one, we need zeta omega n from the characteristic equation. So 4 by 0.5 is 8. And also omega n will be required. So omega n is 8 by 0.591. So basically 13.536. So now based on these values, we can easily find out our desired characteristic that you're looking for. S square plus twice zeta omega n s plus omega n square equal to 0. This should be our desired characteristic equation. So we already know all the required values. So s square plus 2 into 8, that is zeta omega n s plus 13.536 whole square. That will give us s square plus 16s plus 183.223 equal to 0. So whether you have noticed or not, the design is relatively simpler, but the understanding, the comprehension is a bit complicated. So now, since the plant is represented in the phase variable form, we can easily write what should be our the desired characteristic equation based on Si minus A minus Bk. Okay, so from the determinant of this one, we can easily figure out what should be our designed system. So since our matrix is 0, 1, minus 3, minus 5, the system matrix, A minus Bk will eventually give us something like this: 0, minus 3 plus K1, and minus 5 plus K2. 0. So since it is in the phase variable form, we know that the coefficients will be appearing in the characteristic equation in the opposite order. So S square plus 5 plus K2 S plus 3 plus K1. So this should be a characteristic equation. Now we can easily compare the coefficients, and we can see the values of K1 will be, the values of the K is K1 and K2 is basically 180.223 and 11. So this is our design problem. Now, based on this system, if you want, you can also represent in the phase variable form. So you can write something like this: x dot equal to A minus Bk x plus Br, which will be 0, 1, minus 183.223 minus 16 x plus 0, 1 r. And our output equation of y equal to Cx, that is 10x. Now, for the steady state error analysis, for the step input from the chapter 7 that we have seen, that is steady state error analysis can be given by this formula: 1 plus CA inverse B. So this is input specific. So you have to keep in mind, this is for step input. And another general formula that we also have seen was this one, just as a review, is that steady state error was limit s tends to 0 as E of S, and we have seen that our E of S can be replaced by S RS, then 1 minus C into SI minus A inverse B. Okay, so this was general. So whatever your R, based on that, you can have you can use the same equation but with different values of RS. Can be S 1 by S for your step, 1 by S square for your ramp, 1 by S cube for your parabolic input. So go for anyone you like. So in this particular case, we are dealing with the steps, so we can directly go for the step equation. Now, what will be our modification? Our system is basically system matrix is not A here. So 1 plus C, you will have A minus BK inverse B. Now, if you just plug in the values, 1 plus C matrix, our is 1, 0. And our A minus BK is basically 0, 1 minus 183.223. And then you have minus 16. So this A have to be inverse. If you take the inverse matrix of that one, then you multiply with B matrix. So if you do that, you're going to see, use the calculator, then it will give you 0.995. So this is our steady state error. Now, existing steady state error, if we are not inserting a pole at the origin, so finite value of the steady state error. Now, next, what we have to do is, let's look at the second part of the example, and it says that you have to repeat the example with the integral control. So now we have to use with integral control. So, and then finally, again, you have to find out the steady state and the value of that. So let's start with this one. So now the new system and the system will be basically based on this equation. So we can also start it from here. So our B will be x dot equal to this formula. So in our case, what is x? What is our A and B matrix? And so we can easily figure out all this from this equation. So now, directly, if we plug in the new system, we already have two state variable, that is x1, x2. Now we are introducing the third one, xn. So x1 dot, x2 dot, xn dot should be equal to A minus BK. So A is basically 0, 1 minus 3 minus 5A minus BK. So B is 0, 1 and K is K1, K2. So this is A minus BK. With that, you should have your B, that is 0, 1 and K, the new gain that we have introduced after the integral control. Then you have minus C. So basically minus 1, 0, that is minus C and 0. And this will be your state variables x1, x2, xn plus 0, 0, 0, sorry, 0, 0, 1 R. Okay, so after doing a bit of simplification, then what you are going to see is that it will be 0, 1 minus 3 minus 5, then 0 minus K1, 0 minus, we could keep the K1 and K2 later on. We can go for the minus K1, 0, K2, and you have a minus here. Okay. So this is your A minus BK, then you have 0 KE. and you have -1, 0, 0 with x1, x2, xn plus 0, 0, 1 r. Okay, so we can write that this will be 0, 1, then you'll have -3 plus k1 -5 plus k2 0 by ke 0 k and -1 0 0. So this is your new system matrix. Okay, so the state equation is already derived, and what about our output? Output is unchanged, so that is y equal to 1 0 0, your x1, x2, and xn. Okay, so the system that we have already is basically from that existing system. We should look for our closed loop transfer function. We can also figure out our closed loop transfer function, and that will give us also our desired scenario. And also we have said that we have to be careful about the location of the zero. So whether our original system has any zero or not, we should actually figure it out. And our one of the easiest assumption is whatever the location of the zero in the open loop, we keep the same location in the closed loop. So for that, if you want to figure out what is our existing system's location, in that case, we should figure out what is our existing system's transfer function. So the existing system's transfer function can be figured out with the location of the pole of the original system. So for the original system, we can figure out that our system should have a characteristic equation something like this: minus si minus a inverse. So it will be something like this: 0, 1 0 0 1 s minus 0 0 minus 3 minus 5. So just do a bit of tweaking, and then you're going to see that your system will have a characteristic equation like this. One by. So inverse matrix, you can figure out separately, which I haven't done, but you can easily do it, which will be your adjacent of Si minus A divided by determinant of Si minus A. Okay, so based on that, you are going to see if I figure out the equation, and then finally, what you have to do is your closed loop transfer function, that is Ts equal to C into Si minus A inverse P. So this is already covered in one of the earlier lecture how to figure it out. So that is why I'm not doing in detail, just giving you the formula. You just apply those, and eventually we are going to see that it will be 1 by s square plus 5s plus 3. So why we're interested about this one? Because we want to know whether our system has any zero or not. If there is any zero, we place it exactly in the same location, then we validate with our final result. So since the original system has no zero, so in our closed loop transfer function, we also assume that our closed loop transfer function will also have no zero. And the design system will have no zero for this particular case. And also we have already designed the controller and in the section A. So the controllers have a transfer function, s square plus 16s, and the characteristic equation of s square plus 16s plus 183.223. So since our system's order is increased, it has to be third order system. And since there is no zero, we don't have to go for pole zero cancellation. So rather, but we have to take a pole that is far away so that the second order system is not hampered. So our rule of thumb that we have is the higher order pole has to be 5 times or more away. So we can see that more away from the sigma value. So sigma is basically here minus whatever the value we are getting is half of it. So basically 16. So from the characteristic equation minus b plus minus b square root over b square minus 4ac by 2. So 16 by 2 is coming. So that is why approximately 8. So we can also assume that it is far away, and we assume that it is S 100, S plus 100 can be one of the candidate, which is more than whatever necessary. So 5 times away should be good to go. That is 5 into 8. 40 should be good, but we're on the safer side, just following the example given by the book. But as long as it is 5 times 8, it should be okay. Okay, so now you multiply and figure out the characteristic equation that is SQ plus 116 S square plus 1783.1 S plus 18310. So this is our desired characteristic equation. Now we should go for what should be our designed characteristic equation. So that has to come from this new system matrix. Okay, so we can derive in this way what should be our design characteristic equation, that is SI minus new matrix, we say N. Okay, so you have to find out the determinant of this one. Basically, S times 100,010,000 minus 0, 10 minus 3 plus K1 minus 5 plus K2 KE minus 100. Okay, so now what we are having is S minus 10, 3 plus K1, S plus 5 plus K2, K. Then you have 1 0, 0. So the determinant of this one will be S times, this should be S as well. So S times S into S plus 5 plus K2 plus 1 into S into 3 plus K1 plus K should be equal to 0. Okay. So ultimately what we're going to see here is S into S square plus S into 5 plus K2 plus S into 3 plus K1 plus K equal to 0. So from this one, you can easily see that it will be S cube plus S is going to 5 plus K2 plus S3 plus K1 plus KE equal to 0. So now if you compare this equation with our desired characteristic equations and we find out the values of K1, K2, K3, then we're going to see that K1 will be 1780.1, K2 will be 111, and K3 or KE should be 18310. So based on that, we can write our the solution, that is the state equation x1 dot x2 dot xn dot should be equal to 0, 1, 0 minus 1783.1 minus 116 18310 minus 1 0 0 x1 x2 xn plus 0 0 1 r. And our output equation y equal to unchanged 1 0 0, basically a function of x1 only, since we were doing the designing in the phase variable form. Okay, so now you can also validate whether your result is whether your system is having a 0 or not based on your closed loop transfer function, and just figure out that C Si minus a nu inverse with B. So that will give you 18310 S cube plus 116 S square plus 1783.1 S plus 18310. So once you have done that, you can also go for your error calculation, as they're asking for, even though you know that the error has to be 0. So 1 plus e to the minus 1 plus C A inverse, that is nu A in our case, nu A inverse B. So 1 plus C, that is 1 0 0, and inverse matrix 0 1 0 minus 1783.1 minus 116 and 18310 minus 100. that will be inverse with your B matrix, that is 0, 0, 1. And do the calculation, you're going to find that we have designed a system for zero steady state error. So this is the procedure that you should be following specific to a ramp input, but for some other input, we have to go for the generalized equation that we have discussed earlier. Assalamu alaikum.